Okay. Okay, recording this session. Let me What? Yes. For the session, we dropped a couple and gained one. The one I gained ain't here, so we'll work that out. And of course, one student's out on a cross country, which I'll never argue about. If you can get flight time.
I just got back.
Yeah. I'm okay with that, not all the time, but I mean, sometimes you have to fight to get flight time. So if you let me know you're flying, I'll work that out. And I record this anyway, so you can always catch up that way if need be. All right, to start with, let me see. You're gonna, like I said, you're gonna absolutely need your notes in a little bit because we're gonna go through those, and then, okay, that's everybody that's supposed to be here. All right. Like I said, guys, try to get here on time. We're just waiting for Bailey. We'll see if she shows, but she did a course change, so I'm not sure about that. We'll figure that out. Okay, so just real quick, let's don't need this. All right. Just as a review, on the Moodle, let's see, that's a collaborate. There we go. It's participants. Come on. There it is. Now, on the Moodle, if you need to watch anything, if you go up here to the Meteorology Collaborate right there, okay, if you click on it, if you're not here, if it'll come up, come on now. Running slow. Anyway, if you click on it, you will get, there, it's just being slow on me. All of the recordings will be right here, okay? Or if you're absent, you can click on that and join the session if you can join the session during the class time when I'm videoing it. So it's right here. You can do that. And if you want to see Monday's class, again, it's right here as well. So for my online guys, I download this and convert it to a YouTube and then post it to their Moodle. So that covers that. Secondly, let's see, let me get rid of this. What I'd like you guys to do is pull up your Moodle real quick. Let's see, let's go back to here. It's running a little slow. Go back and pull up your Moodle if you've got your computers and stuff handy, and go down right here to the Quizlet join code. All right, we did this in that for those that are in navigation. But go ahead and join this Quizlet classroom. I set up a classroom for you guys, and I do have a couple of Quizlets that we won't do it today, but probably next Tuesday we'll work on the Quizlet a little bit. But go ahead and hit the join code. I was going to do that Monday, but didn't get to it. So right there, hit the join code. And if you're on my online class, you can hit that join code. You'll be in with them. All right. Everybody got that? And if you hadn't got it now, go ahead and, when you get to it, go ahead and do it. All right. All right. So, yeah. And let's wait a second. And for those, there's the Quizlet join code right there. I had to make sure it was on the Moodle right there. You can see it. Okay. This will be the first time I've done a video on the Moodle. Sometimes we have issues with the, if you're trying to watch it online with the audio. Once in a while it won't come through if y'all have done that. If you're watching this online, then if the audio doesn't come through, just these are videos straight off the notes. So just pull up the notes, those links there. You can watch the videos there. So the first one, let's see, right? Is that the one? Let's see, right? Where'd it go? Yeah, this is one out of a 3 series. Let me share it here. Pull it up. Got the right one. Private pilot tutorial. That's it. Where's it? There it is. Okay. And now you can see it on here. So if the audio for some reason doesn't come up, just this is the first video on your notes. So I'll go ahead back and play it. This is a part 1 of part 3 series. The other 2 parts are at the end of the notes. This one's 17 minutes, pretty good, but it gives a good overview of aviation weather. So here we go. Hopefully the audio.
Tutorial 11, Weather Theory. This lesson will cover weather theory. Understanding the theories behind weather helps a pilot make sound weather decisions based on the reports and forecasts obtained from a flight service station weather specialist and other aviation weather services. In any given volume of air, nitrogen accounts for 78% of the gases that comprise the atmosphere, while oxygen makes up 21%. Argon, carbon dioxide, and traces of other gases make up the remaining 1%. This cubic foot also contains some water vapor, varying from 0 to about 5% by volume. This small amount of water vapor is responsible for major changes in the weather. The atmosphere is made up of 4 distinct layers that extend up to 350 miles from the Earth's surface. The first layer is the troposphere, which extends from the surface to 20,000 feet over the poles and 48,000 feet over the equator regions. Most weather happens in this region, and the temperature drops by 2 degrees Celsius for every 1,000 feet of altitude gain. The pressure also drops by an inch for every 1,000 feet of altitude gained. Above the troposphere and before the stratosphere, there is a region called the tropopause. This region traps moisture in the troposphere and the associated weather. Above the tropopause are 3 more atmospheric levels. The first is the stratosphere, which extends from the tropopause to a height of about 160,000 feet. Little weather exists in this layer, and the air remains stable, although certain types of clouds occasionally extend in it. Above the stratosphere are the mesosphere and thermosphere, which have little influence over weather. The atmosphere is in constant motion. Certain factors combine to set the atmosphere in motion, but a major factor is the uneven heating of the Earth's surface. Earth is warmed by energy radiating from the sun. The process causes a circular motion that results when warm air rises and is replaced by cooler air. Because the Earth has a curved surface that rotates on a tilted axis while orbiting the sun, the equatorial regions of the Earth receive a greater amount of heat from the sun than the polar regions. Solar heating causes higher temperatures in the equatorial areas, which causes the air to be less dense and rise. As the warm air flows toward the poles, it cools, becoming denser, and sinks back toward the surface. The unequal heating of the Earth's surface not only modifies air density and creates circulation patterns, it also causes changes in air pressure, or the force exerted by the weight of air molecules. Although air molecules are invisible, they still have weight and take up space. Imagine a sealed column of air that has a footprint of 1 square inch and is 350 miles high. It would take 14.7 pounds of effort to lift that column. This represents the air's weight. If the column is shortened, the pressure exerted at the bottom and its weight would be less. The weight of the shortened column of air at 18,000 feet is a
Okay, what's the units of pressure?
Units of pressure?
Yeah. What they demonstrated here, what the units are they talking about? Pounds per, yeah, PSI. Okay. So that's the English measure. You can also do it by inches of mercury, that's barometric pressure, and you can also do it by millibars, okay, or hectopascals. All right. So keep in mind, pressure is PSI, pounds per square inch, and standard sea level pressure is 14.7 PSI at 59 degrees Fahrenheit, or 1030.2 millibars at 15 degrees Celsius, which is a standard in the metric system, SI system. Okay, but we'll talk about that lots more. But I just wanted you to notice that pounds per what? There it is, square inch, PSI.
approximately 7.4 pounds, almost 50% that at sea level. The actual pressure at a given place and time differs with altitude, temperature, and density of the air. These conditions also affect aircraft performance, especially with regard to takeoff, rate of climb, and landings. The force created by the rotation of the Earth is known as the Coriolis force. This force is not perceptible to humans as they walk around because humans move slowly and travel relatively short distances compared to the size and rotation rate of the Earth. However, the Coriolis force significantly affects bodies that move over great distances, such as an air mass or body of water. The Coriolis force deflects air to the right in the northern hemisphere, causing it to follow a curved path instead of a straight line. The amount of deflection differs depending on the latitude. It is greatest at the poles and diminishes to 0 at the equator. The magnitude of Coriolis force also differs with the speed of the moving body. The greater the speed, the greater the deviation. As shown above, the speed of the Earth's rotation causes the general flow to break up into 3 distinct cells in each hemisphere. This circulation pattern results in the prevailing westerly winds in the conterminous United States. Circulation patterns are further complicated by seasonal changes, differences between the surfaces of continents and oceans, and other factors such as frictional forces caused by the topography of the Earth's surface, which modify the movement of the air in the atmosphere. Thus, the wind direction at the surface varies somewhat from the wind direction just a few thousand feet above the Earth.
Okay, does anybody know about what latitude North Carolina is? Looking at this, just looking at it, eyeball it. In the 30s, yeah, 36 to be precise. Okay, so what direction is our prevailing weather? Well, we had storms go through yesterday, right? West to east, yeah. Because if you look up here really quick, okay, here we are, right here. And again, the prevailing weather, if we want to know what it's going to do, comes this way. Okay. From the equator up to about 30, though, it's actually in the opposite direction. Okay. It goes this way. Okay. And that causes this area to have northeast prevailing winds in the weather. This is why, hey, you get a hurricane, right? across the Atlantic. And then when it gets north, what's it do? Swings out the other way, just like that. Makes sense when you look at the prevailing winds. Anybody been to Hawaii? What's going on in Hawaii right now?
Fire, of course.
Yeah. Which island were you on?
Main forest.
Military?
A lot of.
Okay,
Yeah.
then you were on Oahu and Schofield Barracks or Shaft, or one of those two if you're on. Okay. Well, if you're on Oahu, you go on the north shore of Oahu, right? Kaneohe, Kailua, that area. When you look up at the mountains, and what's it look like? Beautiful green, right? Oh man, I mean it is green. You'll see the streams coming off the mountains, and they get all kinds of rain on that side of the island. What about the Honolulu side?
I remember those like one train.
Yeah. Okay. So what's going on in Maui right now?
Fire.
Yeah, the fires, and it's not, here's Oahu. Okay, it kind of goes like this, goes about down like this, got Pearl Harbor, okay, goes down like this. How do I do? Look like it? Okay. Then you got Molokai here, Lanai, Kaho'olawe, and then you got Maui like this. Okay. There's two main volcanoes on Maui. Which way do we say the trade winds go?
They're going west to east.
West to east, and they're basically northeast trades like this. All right, coming off the ocean, right? This is why I said, well, you said, here's the mountains going down like you said, Oahu. You said over here you got all kinds of clouds and stuff. Why? Because that wet, moist air comes in and hits the mountains. Which way does it go when it hits the mountains? Up. Okay. And so when it rises, it loses temperature. The temperature goes down, right? About, we said 2 degrees per Celsius per 1,000 feet. And it also, the pressure comes off it. So what's it do? Any moisture in that air condenses. Okay. This side of the island, that moisture gets dumped out onto the mountains. So this side of the island is just semi-arid. Okay. Well, look at here. Where were most of the fires? In Maui, in Lahaina, which is on the southwest coast. Okay? Is it any surprise that it was really dry? No. Okay? Because basically, you look at the weather patterns, northeast trades will bring the moist air in, it'll hit those mountains, dump the rain on the mountains, and basically you have what's called a rain shadow on the downwind side. We'll study that a little bit later, but that's what's happening. But that's a result of the prevailing weather patterns. Doesn't it? How about that? Make sense when you look at it like that? Okay. Let's move on. Pressure.
Atmospheric pressure is typically measured in inches of mercury, Hg, by a mercurial barometer shown on the left. The barometer measures the height of a column of mercury inside a glass tube. A section of the mercury is exposed to the pressure of the atmosphere, which exerts a force on the mercury. An increase in pressure forces the mercury to rise inside the tube. When the pressure drops, the mercury drains out of the tube, decreasing the height of the column. This type of barometer is typically used in a laboratory or weather observation station, is not easily transported, and difficult to read. An aneroid barometer, shown on the right, is an alternative to a mercurial barometer. It is easier to read and transport.
Where do you find one of these in an airplane? Every airplane has one. Come on, my pilots. Huh?
What are you talking about? What do you find?
Where do you read your altitude? Altimeter. Yeah. You have a static port, which lets in the air, right? Then you have a sealed aneroid cell. When you go up, what's the air in the cell do? It expands. Yeah, because the pressure's going down on the outside. Then when you come down, it contracts because the pressure's going up. Hey, just hook it to a needle, and what have you got? An altimeter. Okay, so right off the bat, you know that an altimeter simply reads barometric pressure, exactly like this. Okay, in fact, that's what the inside of your altimeter looks like. Okay?
The aneroid barometer contains a closed vessel called an aneroid cell that contracts or expands with changes in pressure. The pressure sensing part of an aircraft altimeter is essentially an aneroid barometer. It is important to note that due to the linkage mechanism of an aneroid barometer, it is not as accurate as a mercurial barometer. To provide a common reference, the International Standard Atmosphere, ISA, has been established. These standard conditions are the basis for certain flight instruments and most aircraft performance data. Standard sea level pressure is defined as 29.92 inches of mercury and a standard temperature of 59 degrees Fahrenheit, 15 degrees Celsius. Atmospheric pressure is also reported in millibars, with 1 inch of mercury equal to approximately 34 millibars. Standard sea level pressure is 1013.2 millibars. Typical millibar pressure readings range from 9.
Now, when you get your weather briefings, right, guess what? You get your pressure in millibars, and you get your temperature in centigrade. Okay, so get used to it.
950 to 1040 millibars. Since weather stations are located around the globe, all local barometric pressure readings are converted to a sea level pressure to provide a standard for records and reports. To achieve this, each station converts its barometric pressure by adding approximately 1 inch of mercury for every 1,000 feet of elevation. For example, as shown above, a station at 5,000 feet above sea level with a reading of 24.92 inches of mercury reports a sea level pressure reading of 29.92 inches of mercury. Using common sea level pressure.
So what's going to happen if you're sitting on the tarmac right at Denver? Guys, 45 your computers right now. Okay, you don't need it right now. Put it at a 45. Okay. And you put 2992 and your field elevation is 5,800 feet. What's your altimeter going to read? If that's the proper pressure. Huh? Yeah. It's going to read 5,800 feet, isn't it? Yeah. Okay. So don't think, hey, man, when I'm going to land, my altimeter is going to read 0. No, even here, over here, your altimeter when you land is going to be about 460 feet. Right? For those that have flown over here. Right? This is why your traffic patterns at 1,500 feet, which is usually about 1,000 feet above, you know, for a GA aircraft is about 1,000 feet above the airfield. Okay, now does that make sense? What they're trying to say here? That's all they're really saying is when you get to the field, you're going to read field elevation. Okay, if you put 2492 in your altimeter, it would read 0. If you put 2992, it's going to read that 5,000 feet. Well, you want it to read the 5,000 feet.
Readings helps ensure aircraft altimeters are set correctly based on the current pressure readings. As pressure decreases, the air becomes less dense or thinner. This is the equivalent of being at a higher altitude and is referred to as density altitude, dA. As pressure decreases, dA increases and has a pronounced effect on aircraft performance. Altitude affects every aspect of flight, from aircraft performance to human performance. At higher altitudes, with a decreased atmospheric pressure, takeoff and landing distances are increased, as are climb rates. When an aircraft takes off, lift must be developed by the flow of air around the wings. If the air is thin, more speed is required to obtain enough lift for takeoff. Therefore, the ground run is longer. An aircraft that requires 745 feet of ground run at sea level requires more than double that at a pressure altitude of 8,000 feet, as shown in the figure above. At sea level, atmospheric pressure is great enough to support normal growth activity and life. By 18,000 feet, the partial pressure of oxygen is...
Okay, one thing I do, let's see, listen up. If I can get it going, hang on. They wasn't working on it?
Not what you call it. There you go.
That's the altitude. Okay. So they said density altitude varies with temperature and humidity, right?
Right.
And what they were talking about, how is your airplane going to act today? Take off KSOP. Is it going to act like it's at 469 feet or is it going to act like 27?
2,300.
Exactly, or whatever the PA was. 2,300. Okay. Everybody see the difference, especially during the summertime. You got to pay attention to that, especially the helicopter pilot. Okay. All right. Are we relating it to aviation? That's what I want to be doing. Okay, about another 7 minutes.
reduced and adversely affects the normal activities and functions of the human body. The reactions of the average person become impaired at an altitude of about 10,000 feet. But for some people, impairment can occur at an altitude as low as 5,000 feet. The physiological reactions to hypoxia or oxygen deprivation are insidious and affect people in different ways. These symptoms range from mild disorientation to total incapacitation, depending on body tolerance and altitude. Supplemental oxygen or cabin pressurization systems help pilots fly at higher altitudes and overcome the effects of oxygen deprivation. Air flows from areas of high pressure into areas of low pressure because air always seeks out lower pressure. In the northern hemisphere, the flow of air from areas of high to low pressure is deflected to the right and produces a clockwise circulation around an area of high pressure. The opposite is true of low pressure areas. The air flows toward a low and is deflected to create a counterclockwise circulation. High pressure systems are generally areas of dry, stable, descending air. Good weather is typically associated with high pressure systems for this reason. Conversely, air flows into a low pressure area to replace rising air. This air tends to be unstable and usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. A good understanding of high and low pressure wind patterns can be of great help when planning a flight, because a pilot can take advantage of beneficial tailwinds shown above. When planning a flight from west to east, favorable winds would be encountered along the northern side of a high pressure system, or the southern side of a low pressure system. On the return flight, the most favorable winds would be along the southern side of the same high pressure system or the northern side of a low pressure system. While the theory of circulation and wind patterns is accurate for large-scale atmospheric circulation, it does not take into account changes to the circulation on a local scale. Local conditions, geological features, and other anomalies can change the wind direction and speed close to the Earth's surface. Different surfaces radiate heat in varying amounts. Plowed ground, rocks, sand, and barren land give off a large amount of heat. Water, trees, and other areas of vegetation tend to absorb and retain heat. The resulting uneven heating of the air creates small areas of local circulation called convective currents. Convective currents cause the bumpy, turbulent air sometimes experienced when flying at lower altitudes during warmer weather. On a low-altitude flight over varying surfaces, updrafts are likely to occur over pavement or barren places, and downdrafts often occur over water or expansive areas of vegetation, like a group of trees. Typically, these turbulent conditions can be avoided by flying at higher altitudes and even above cumulus cloud layers, as shown by the image above. Convective currents are particularly noticeable in areas with a landmass directly adjacent to a large body of water, such as an ocean, large lake, or other appreciable area of water. As shown by the top images, during the day, land heats faster than water, so the air over the land becomes warmer and less dense. It rises and is replaced by cooler, denser air flowing in from over the water. This causes an onshore wind, called a sea breeze. Conversely, at night, land cools faster than water, as does the corresponding air. As shown by the bottom image, the warmer air over the water rises and is replaced by the cooler, denser air from the land, creating an offshore wind called a land breeze. Convective currents can occur anywhere there is uneven heating of the Earth's surface. As shown above, convective currents close to the ground can affect a pilot's ability to control the aircraft. For example, on final approach, the rising air from terrain devoid of vegetation sometimes produces a ballooning effect that can cause a pilot to overshoot the intended landing spot. On the other hand, an approach over a large body of water or an area of thick vegetation tends to create a sinking effect that can cause an unwary pilot to land short of the intended landing spot. Obstructions on the ground affect the flow of wind and can be an unseen danger. Ground topography and large buildings can break up the flow of the wind and create wind gusts that change rapidly in direction and speed. These obstructions range from man-made structures like hangars to large natural obstructions such as mountains, bluffs, or canyons. It is especially important to be vigilant when flying in or out of airports that have large buildings or natural obstructions located near the runway. The intensity of the turbulence associated with ground obstructions depends on the size of the obstacle and the primary velocity of the wind. This can affect the takeoff and landing performance of any aircraft and can present a very serious hazard. During the landing phase of flight, an aircraft may drop in due to the turbulent air and be too low to clear obstacles during the approach. This same condition is even more noticeable when flying in mountainous regions. As shown above, while the wind flows smoothly up the windward side of the mountain, and the upward currents help to carry an aircraft over the peak of the mountain, the wind on the leeward side does not act in a similar manner. As the air flows down the leeward side of the mountain, the air follows the contour of the terrain and is increasingly turbulent. This tends to push an aircraft into the side of a mountain. The stronger the wind, the greater the downward pressure and turbulence become. Before conducting a flight in or near mountainous terrain, it is helpful for a pilot unfamiliar with a mountainous area to get a checkout with a mountain-qualified flight instructor. Please help us spread the word about.
Okay, so that was part one, which is that's a three-part series. Go ahead and if you would grab your notes that I handed out. Let's take a look at those things. Let me pull it up, and then we'll see. preview them real quick. Where's my notes? There they are. Module 1, there it is. Okay, so the first thing we're going to look at, let me make that a tiny bit bigger. There you go. The two places where you need to read for this section will be the circular, which I call it the handbook. I put it in, who wanted hard copies? I had at least 5 people that wanted hard copies. I put in for it. He's copying it now. We should have it by Tuesday. And so when you come in Tuesday, you'll have that. For right now, work off the PDF copy. But we got the circular here in chapter 4, which is really short. And then you should be working off also 6A, which is chapter 6A in the JEP. Okay, and that's posted on Moodle as well. And we're going to look at the basically what they talked about in the video. That's why I put the video right there. We'll talk about the construct, if you will, of the atmosphere and the main characteristics. So that's what we're going to talk about first off. This second video here, I actually posted this morning. I'm not sure if I'm going to play it in class or not. It talks about the layers of the atmosphere. I'm going to hit that a couple times, and if I don't hit it, but you won't find this on your notes, of course, because I just added it this morning. So a lot of times as I'm going through prepping for class, if I find something else to put in the notes or something, I'll update them. But that one there's not there. This reference link right here, CFI notebook, there it is. It's got a whole set of supplemental readings about what we're going to cover. Okay. And I mean, exactly what we're going to cover right now. So if you want some supplemental reading, this is just what the video covered, isn't it? Temperature, well, we'll talk about pressure. We'll do that probably next class. We'll start with pressure. Okay. So that's, this is the CFI notebook. All right. If you want a site that you can reference, if you're getting ready for a CFI check or a commercial check or something like that, CFI notebook is really, really good. Okay, great study site. All right, anyway, back to that. So what I'll do now is, with your notes, compare it to what I'm going to cover in the PowerPoint real quick, because that's what we'll do next. I'm going to run through this PowerPoint real quick. The first about third of it. There's 27 slides in the PowerPoint. Where'd it go? YouTube, and it is weather module 1. So there it is, PowerPoint. All right, that should be showing up. Slideshow from the beginning. Okay, so now I can get up and move that along. Okay, so talking about, back up, again, specifically for this one, chapter 6A and chapter 4, gotta change that weather budget. It's chapter 4 now. See, now I gotta update my, the handbook's a little bit different, so I gotta update that. So chapter 4 and then chapter 6A, and I'll fix it. All right. Again, atmosphere is a cloud of clay gas, suspended particles that surrounds the Earth. Up to about 6,000 miles, you have a appreciable atmosphere. Thicker at the surface and then thins with altitude. Why? Why is it heavier at the surface? What holds the atmosphere to the Earth? Big G, gravity. Okay, so the closer you get to Earth, the higher the gravity. You know, if you look at Newton's gravitational formula, you know, it's an inverse square of the distance. Right? So the closer you get, the more gravity you have. So the closer you get to the Earth, the atmosphere, in fact, is getting pulled harder. And so the pressure closer to the surface is much, much higher. Okay, so it's telling you, yes, lower layer based on, if I ask you, hey, how do they establish the layers of the atmosphere? And I do ask you that in a quiz. Okay, it's based on what? What the temperature is doing in that layer. We'll talk about each one. So, again, the layers are defined by what the temperature change is within that layer. By the way, the temperature change will determine the properties of the layer, won't it? There's a couple things. We'll talk about that. Again, protects the Earth from harmful radiation from the sun. Again, sucks up a lot of IR. Infrared sucks up a lot of X-ray and UV. And we'll talk about what each layer of this atmosphere does. Regulates the Earth's surface by absorbing, re-radiating, and circulating heat from the sun. Okay, and that's what the atmosphere does. It holds moisture that creates, okay, the only reason we have weather here is because there's moisture. Okay, if you go to the stratosphere, there's not any weather. The only way you get weather in the stratosphere generally is you got a thunderstorm that pops up, past about 30,000 feet. Then you've got weather in the stratosphere. But other than that, the stratosphere is stable. Good reason. We'll talk about that later. Okay? What is the atmosphere made of? All this stuff. Kind of interesting. I like what they said in the video about most people think that the atmosphere is mostly oxygen. If the atmosphere was mostly oxygen, we would probably burn up. Because oxygen supports fire, okay, combustion. Nitrogen, okay, nitrogen is fairly neutral. If anybody put nitrogen in tires, a lot of sports cars and stuff will put nitrogen in their tires. Why? Because it's actually more stable than the mixture of air. Okay, so you'll see that sometimes. So what does nitrogen actually dissolves oxygen and dilutes the oxygen content. So it's funny because the oxygen, the O2, is actually dissolved in the nitrogen, just like sugar is dissolved in sweet tea. Kind of cool, huh? All right. Okay, and of course, oxygen that supports combustion, supports life, and comprises only 21% of the atmospheric gas volume. Okay, so 78% is actually nitrogen. So what's going in and out of your lungs right now? It's mostly nitrogen. 78% nitrogen. Only 21% of it is oxygen, but your body is tuned, if you will, to break out the O2 molecules and use it. Same thing for plants. Okay, they're actually tuned to pull in the CO2 and to kick out O2 molecules. Okay. Argon again is neutral. Again, that helps the atmosphere. Each gas has their own function, doesn't it? So the argon actually helps the atmosphere to be stable. Okay. CO2 again supplies the fuel, if you will, for photosynthesis, and also is part of the greenhouse gases. And it helps keep the Earth warm and stable. Anybody know the average temperature of the Earth all over? If I were to take all the temperatures, what's the standard temperature? Huh? 15 degrees Celsius or 59 Fahrenheit. They came up with that because that's the average from the poles to the equator. The average temperature of the Earth all around is about 15 degrees Celsius or 59 degrees Fahrenheit. All the other gases are about 0.04%. That's pretty small in volume, but there's a lot of water. Okay, up to about 4 to 5%. Okay, of the atmosphere is also water. And here's just a list of all the oh, by the way, gases: helium, methane, krypton, sulfur dioxide, hydrogen, nitrous oxide, xenon, all of those. Okay? Ammonia. So, by the way, anybody, science, Jeopardy question: what is the most abundant gas in the universe? Huh? Yeah, hydrogen. There you go. Hydrogen. The sun's mostly made of hydrogen and helium. Right? So yeah, most nebula are hydrogen and helium. All right, and in fact, the byproduct of the sun making its heat, it burns and fuses the hydrogen, and the byproduct is heat. Okay. Okay, y'all cool with this? Who knows? So weather, well, here's some definitions. I would definitely know that. I think that's on your notes too, if you're looking at your notes. Okay, weather again is the state of the atmosphere at a given place and time. Whereas climate, the difference that is climate is the given average, if you will, weather state over a long amount of time. Okay. When we look at weather, we talk about an air parcel, okay, which basically 1 cubic centimeter. Anybody know what a cubic centimeter is? Like you think? Yeah, that's about a cubic centimeter. But what we do is we define that cubic centimeter and say, all right, this is a parcel of air, and what is it doing? What is that parcel of air doing? Tell you, if you don't remember anything about this course, okay, I want you to remember that what happened, Ian, what happened to the moist air when it hit the mountain? It went up. What happened? It condensed, it made clouds, and it rained. You don't remember anything else, anything that causes a piece of air parcel to rise, whatever that cause is, will generally create clouds, cloudy weather. Okay? So, and it can be, what that, by the way, that's called orographic lifting. That's the terrain actually lifts the clouds. But there are a lot of other causes, if you will, that causes air to rise. Okay? Especially this time of year. Right? The ground gets hot. The air at the ground in North Carolina, we get afternoon thunderstorms in the summer. You'll wonder why they're in the afternoon. Because of that convective lifting. The ground heats up, causes the air to go up. Okay? Oop, storms, kind of like yesterday. Although yesterday was, I think, a front passing. So you're telling me a cold front causes the air to rise? So you get crappy weather.
Funny story. I'm from Brazil.
Yep.
And I've never been there, but in the Northeast, Northwest, like in the house, or that area, it's like tradition, 4 o'clock shower, like every day in the afternoon.
Yeah.
I'm more from the south, so in the summer it's more common, but there since they're much greater, so every day are off.
The other thing about the tropics like that, remember in the video they said, hey, there's usually an equatorial low, right? What do we say about low pressure? What does it make air do? What happens when air goes up? You know, it cools, the pressure comes off, and you get clouds. Now it's kind of crazy though, and we'll talk about it later. I'm probably getting ahead of myself, if that's okay. The Earth is tilted, right? 23 and a little bit, I think 23 and a half. All right. And so during our summertime, we're tilted towards the sun, right? During the southern hemisphere, 6 months later, they're tilted towards the sun, and we're tilted away.
Summer in Brazil and Australia.
Yeah.
Christmas is summer.
So, I mean, yeah, so what does that do? Here, I'll do there. What does that do to the direct sunlight? It goes north in the summertime and goes south by 23 degrees till the tropic of Cancer and tropic of Capricorn. So that direct sunlight in the spring and the fall falls on the equator. Okay? Summertime, it goes up here 23 degrees. You're getting the direct sunlight. Wintertime, okay, you're getting it over here. It should be in the southern hemisphere. You hear what I'm saying? You understand what I'm saying? So we know there's already an equatorial low. So what's that equatorial low going to do? Will it move with the sun? Because isn't it the sun heating that's creating that equatorial low? So if you look at a satellite view, you'll have, in the fall and the winter, you'll have a whole band of clouds right around the equator. And it's raining all the time there. Okay, about 10 degrees north, 10 degrees south. It is raining all the time. During the summertime, our summertime, that whole cloud layer, guess what, moves up. So now you've got a whole line of clouds around the, like that. Anybody heard of the monsoon? Okay. Especially in like sub-Saharan Asia, Indonesia, Southeast Asia, the savannas in Africa, Brazil, right? Because during their summertime, guess where the cloud layer goes? All the way around, and they're gonna get about 2 months of rain constant. Okay, in their summertime, our wintertime. And up here, they're going to get about 6 or 7 months of almost no rain. Okay, unless it's locally produced. So that whole, if you will, that whole band or that low pressure system that causes the air to rise, boom, moves north and south. Okay. Everybody see why? And like I said, I think I got ahead of myself. But that's okay. All right, so the air parcels, in this case, are going to rise. If I have a high pressure system that causes the air partial to come down, kind of on the downside of the northeast trades that we talked about, the air is going to descend. Right? This is why on the the windward side of an island that has a mountain, you're going to see lots of rain, like on Molokai, like on Oahu. On the leeward side, the downwind side, the air is descending. Well, what happens with air descends? Pressure goes up, temperature goes up, and any clouds that you might have vaporize. Okay? So you get what's called that rain shadow. Okay, so we talked about the atmospheric structure and the layers, okay? And I said, all right, we're going to look at each layer. What happens to the temperature in each of the layers? It's not, I think it's interesting what happens, okay? So the layers are the troposphere, stratosphere, mesosphere, thermosphere, and then exosphere is outside. Another name for the thermosphere within the thermosphere is called the ionosphere, and we'll talk about that. Troposphere, okay? If you look at the temperature, this is the temperature line, okay? And so, okay, here's another quiz question. You don't even ask it. Divided in layers based on the changing properties of the changing altitude. Primary characteristic is temperature. Okay. So in the troposphere, right here, we said standard temperature is about 15 C, right, at sea level. As we go up, we said it drops about 2 degrees every 1,000 feet. So sure enough, it's going to drop right here until you get to a point at about 20,000, depending on where you're at, 20 to 30,000 feet. Then all of a sudden, the temperature stops dropping. In other words, it pauses. So they call that the tropopause. Okay? And of course, the troposphere is, there's another good quiz question, is the only layer that has water. Okay, that has water vapor. So if it's the only layer that has water vapor, it's the only one that can produce clouds. And if it's the only one that can produce clouds, then it's the only one that can make weather. Okay? So nearly all the moisture is, in fact, in the troposphere. And again, we talked about the height is 11 to 12 miles at the equator. It's a little bit, it's 5 to 6 miles, though, at the poles. How come? Why is it lower at the poles? Colder. What do we know about colder air compared to warmer air, density-wise? Much more dense. Okay, so what that does, it brings down the top of the troposphere. You ever notice in the wintertime we don't get like convective storms here as much? Okay, because guess what? During the wintertime it's cooler. Guess what the troposphere does?
One way to remember that from purpose class was cold, you want to be together. So then that's the on very close. Summer you want to
Yeah.
so that's why the first one. That's how I remember now.
There you go.
Kind of little notes to remember.
So yeah, but the top of the troposphere actually varies, and it goes up and down the season, and it goes up and down with temperature, generally between 30 to 50,000 feet. Okay, now where we're at, it's going to be about 35,000 feet at our latitude that we're flying. Okay. So cold and dense air at the top of the troposphere, cold, causes it to descend. So it does make it kind of stable, but not, because you also get varying structures and varying situations caused. Okay. The altitude where the temperature stops falling, that's right here, up about 10 to 11 miles, again, is a tropical pause. The temperature falls. Right down here at about minus 40 to 60 degrees down. Okay. That's pretty cold. This is why, if they climb up to Mount Everest right here, right, about minus 30 degrees, why, yeah, you got the snow, and they bundle up and carry oxygen bottles and hold it right at the top of the peak there. Yeah. Okay. Now, but it's kind of crazy. When you get into the stratosphere, look at this. What's the temperature doing? Going, yeah, it's actually becoming warmer. You actually got it. Okay? And inversion is when it's warmer on top than it is on the bottom. We'll talk about why. Okay? So up to about 50 kilometers, 31 miles, the temperature will stop going up, or will stop going down, excuse me. And then that's where the tropical pause is, and then starts going up. What causes air temperature to rise? Heat of some sort, or you're absorbing energy. Go ahead. Where is it getting its heat? Huh? Yeah. Part of that ultraviolet. Okay. So what's in the stratosphere that can suck up UV? Not O2, O3. There you go. Ozone. Okay. So the ozone layer, which is an O3 molecule, is in the stratosphere, and that O3 molecule is really cool when you want to breathe it. It's a little killy if your body can't break down that third oxygen atom. But the shape of that O3 molecule matches the frequency, if you will, because UV is electromagnetic energy, right? Ultraviolet radiation. But the shape of that O3 molecule matches the frequency of ultraviolet light perfectly. Okay? And so it sucks up, if you will, a good part of the sun's UV radiation because it has ozone, VO3 molecule, which I think is like way cool. And because this area right here, the temperature is really stable right here. Where do you think the airliner slide was? Right in there. Yeah, about 30 to 35,000. All right. And like I said, unless there's a thunderstorm, like a big Midwest thunderstorm that'll push up to about 50,000 feet, some of those things. And I remember one cross country we were flying from California to Florida, and we're up at 25,000 feet. We're looking out over Texas, Oklahoma, all that. Holy crap! Thank God we could see those things, right? But sure stuff didn't want to fly out. Yeah, amazing. Some of the storms you'll see out in the Midwest. All right. Anyway, there's little to no water vapor in there, so I guess unless a thunderstorm breaks into it, you're not going to create weather. It has the ozone layer. Oh yeah, you read the PowerPoint. So they absorb the UV radiation. So that's why the temperature rises. So it makes it very stable. It's an inversion layer. Actually holds temperature, aircraft carrying lower stratosphere, large thunderstorms can be up in there. But then, of course, all of a sudden, just like the tropical clouds, you'll get to a point up here at about 50 miles where the temperature will stop going up. It'll actually go from about minus 40 or minus 50 up to about 0. Okay, so it's almost the same as, up here at about 10,000 feet or so. All right, so all of a sudden the temperature stops going up again because you're running out of ozone. And then the temperature starts dropping. Yeah. And it makes sense because you're transitioning. Okay, temperature's dropping, all of a sudden it stops dropping, temperature's going up, stops going up. Okay, that's your transition to the mesosphere. Oh, here we go. Now the mesosphere is important to us because I call that the meteor catcher. Okay. It's really thin, but it's thick enough to create friction for falling objects coming into the atmosphere. So if we have meteor showers, if we have the space shuttle Columbia that broke up there, but yeah, it's thick enough to actually create enough friction to burn up. It's thin, and there's no ozone, so the temperature drops like a big dog. Count about minus 100 down. Okay. So there's enough air particles to create friction, and then it generally protects the Earth from falling space objects. So if the International Space Station, they decided to deorbit that thing, by the time it would get to the bottom of the mesosphere, it would probably mostly burn up. Okay, sometimes there's stuff that's fine, but it's kind of like thermosphere contains the ionosphere. It's kind of what's happened to the temperature again? Yeah, it's pausing, right? In the mesopause, right? And then all of a sudden, what's happening? You're getting out of the atmosphere, so you're getting directly. Okay, you're exiting the atmosphere, so you can get up to a couple thousand degrees out here in the sun. Kind of crazy on when you get up, if you're going from here to the moon, and the engineers had to figure out, hey, if I'm on the sun side of the spacecraft, I'm at really high temperature. Same thing on the moon. Okay, if I'm on the sun side of the moon, it's really hot. If I'm on the cool side, it's like negative 200-300. I mean, so the engineers have to deal once you get out of the atmosphere with extremely high temperatures and extremely low temperature, even sometimes. Okay. So again, the upper atmosphere, high levels of UV and X-ray. And what are these right there? Anybody recognize that? Yes, northern lights or auroras. And where the auroras come from is charged particles from the sun hit the Earth's magnetic field. They're magnetic. And so when they hit the magnetic field, they basically go right and left, and they come in at the northern latitude. And they come into the ionosphere. And when those charged particles enter the ionosphere, they charge any gases that are up, that height. And guess what charging the atmosphere or those gases makes it glow? Okay. So charging hydrogen, I think it glows red. Charging oxygen, I think glows green. Each gas has its own, when it's charged, has its own color that it glows. I think oxygen, nitrogen, red. Anyway, but each gas has its own color. And as those charged particles come into the atmosphere, and this is, by the way, where also the atmosphere will screen a lot of charged particles and a lot of X-ray electromagnetic. So that's another protection design, if you will. Okay, let's see. Most spacecraft and low altitude spacecraft are actually in the thermosphere. Okay? Or they're on the border, if you will, about 140 miles. So the International Space Station, I think, is about 5 miles. So they're right on the edge, if you will. What else we got? Exosphere is outside of exit. So again, you're about 1,000 kilometers or out to about 60 miles. You still get a slight bit of friction from the atmosphere, even outside of the thermosphere. This is why, over time, they have to adjust the orbit of the space station. Low altitude satellites, they actually have to adjust the orbit. One of the things that they're looking at is like a mile-long cable. They can string it out there, and it will create its own magnetic field. And that magnetism will create a little bit of satellites in orbit. So they're experimenting with that. And if you don't have that, then you got to go put out some gas. All right. So generally, there will be an mesosphere outside, especially if you're in a geosynchronous. Let's see, what else we got? Again, minus 273 on the shade side, 2,000 degrees on the sun side. Last thing I'm going to talk about is the standard atmosphere. Now, they mentioned ISA in videos, right?
Yes.
Okay. That comes from the ICAO, if you will, or ISA, or there's an ICAO standard atmosphere. Now, what do they set for? And I gave you a chart on the back of your notes. Okay, that's the ICAO standard atmosphere. And basically, that's for engineering. Okay, it is a benchmark, if you will, for the atmosphere. Now, is the atmosphere really like that? On average. Okay, but on a constant day-to-day, is it really like that? No. Okay, but those are kind of the average. In fact, pull your chart and take a look at it. And you can actually say, all right, on average at 25,000 feet, you can tell what the pressure is going to be. Okay, SI. And this one, you can tell what the density is going to be. They're normally ratios. Okay. So if you look at sea level, all the ratios are 1, right? Didn't we say at about 18,000 feet, the pressure is about half? So look on your chart and check the pressure ratio for 18,000 feet. About 25? Roughly, okay. That's a good benchmark. Okay, how about the speed of sound? Okay. Looking at, I think it's the far right column. What's the speed of sound in knots? I guarantee, well, they might have something like this. What's the speed of sound in knots at 18,000? Say again. 620 knots or miles per hour? Knots, okay. All right, so you got to pay attention to that, because I tell you on the test sometimes they'll throw miles per hour or knots. Okay, or statute miles and nautical miles. You got to watch that on your test. Okay. Okay. I think I'm going to stop on circulation. Because we're out of time. But they covered a little bit of what we're going to cover next on your general circulation. And I touched on it just a tiny bit. So what I want you to do is finish reading and getting your notes for basically 6A and chapter 4. Get those done. I think the 6A exercises will be on the 22nd. Did I say that? Yeah,
It's still pretty good.
I think that's so get those done. Keep working on your notes, and they'll review as well. Questions and everything else? You good? Rock and roll, guys. Thanks. All right. We'll see y'all. See you in NAV tomorrow, most of you. Okay.